guys, we're going to move into 6.3. This is the notes for 6.3, applications of normal distributions. So unfortunately not all distributions are standard normal. So what we're going to do in this section is work with distributions that are not standard. So that means either one or both of these is the case. We don't have a mean of 0, our standard deviation is no longer 1. So what this is basically saying is we can use a z-score to convert our data from whatever it was back to the standard normal. Alright, this is called standardizing your data. Transforming what we had, that's our x's, transforming it to z-scores. Now we have the z distribution, or the standard normal distribution. So here's a visual of it. Non-standard normal means whatever the mean is. X is just some value from the data set. The area to the left of x, that probability we're less than x, can be standardized via the z-scores. Alright, take that x, subtract the mean, divide by whatever our standard deviation is, and now we've got a mean of 0, and that value there, x, whatever it was, is no longer x, it's z. It's basically, now we're finding out how many standard deviations measurements are from the mean, rather than what they were exactly. Alright, that's the transformation that we make. Alright, so here's a typical problem from this a normal distribution problem. Now there's a lot of fluff to this problem. Actually, the meat of it comes right here at the end. The weights of men are normally distributed with a mean of 172 pounds, standard deviation 29. If one man is randomly selected, what's the probability he weighs less than 174 pounds? Given this is the mean and this is the standard deviation. So what we're going to do is we're going to take that 174, alright, and we're going to convert it to its z-score. 174 minus the mean of 172 divided by 29 is equal to 0.07. So this is the regular the regular line representing our data, and we've taken that x of 174 and we've made it its corresponding number of standard deviations it is from the mean. Okay, so it's not even a tenth of a standard deviation from the mean. Alright, notice the 172 is now corresponding to 0. We're on the z-scale. These are z-scores. This is how far these values are from the mean. The mean is no units from the mean. Alright, 174 is 0.07 of these 29s from the mean, just to verify, just so you can see it. If I take 172 and I add 0.07 times 29, I get roughly 174. So that's what we're saying here. Okay, so the area that's to the left of 0.07 I can find via the normal CDF. Alright, negative 9999, comma, where does the shading end? It ends at 0.07 in the z distribution. Okay, remember that's what normal CDF uses, the z distribution initially, and we're getting 0.5279. So that's where that number's coming from. So this is the big thing for you to get down. The probability the weight was less than 174 is equal to the probability that z-score is less than 0.07. That's the big gist of what we're trying to say right here. The key concept is that we can use a simple conversion, the z-score, allowing us to standardize any normal distribution, so the same methods from the previous section can be used. Right? That's what we just did right here. Oops, sorry, right here. When we changed that to the z-scores, and we found the area using the same thing we did in 6.2. Alright, and then some helpful hints. Z-scores, because when we're right here near the mean, z-scores can be between 0 and 1. If we're close to the mean but a little bit above it, we could see a z-score that has that same range of values that a probability does, or the areas will in this case. So be very careful, don't confuse those two. Alright, z-scores are distances along the horizontal scale. Areas are regions under the curve, so you got to be careful. Alright, and then make sure when you're sketching these things that you're on the correct side of the graph. Make sure that you're drawing your sketches correctly, because that's going to be essential for everything. Alright, and then your z-scores have to be negative. A sign error is not like a partial credit here. A sign error is huge. you're going to be on the wrong side of the mean if you don't have a negative when you need one. Alright, and then all your areas and probabilities are positive or zero. They can never ever be negative. Okay, remember the probabilities. A negative probability doesn't make sense. Alright, so using the data from the previous example is the mean weight of men. 172 is the mean, remember that one. And determine what weight separates the lightest 99.5 from the heaviest 0.05. So this is similar to in the last homework set when we were doing the Z alpha stuff. This is the upper 0.005 area, the lower 0.9950 area. Alright, so if you recall, inverse norm is what takes in area to the left and returns the z-score that has that area to the left. So 0.995 gives me this number, alright, 0.2575. That's what they're putting down here. And that's the z-score. Alright, but remember, this is our formula for a z-score. I can do a little bit of algebra here and solve this thing for x. So I'm going to multiply both sides by the standard deviation. Now I got x minus the mean equals z times the standard deviation. And then if I add that mean over to the other side, I get a way to find x if I know a z-score. So what this is saying is, to find x, the thing that we're looking for, I can take that z-score of 2.575 and I can add to it, multiply it by the standard deviation, which was in this 29, if you recall back to what we were doing before. So I can multiply that by 29 and then add the mean of 172, and I get 246 point roughly 7. Alright, there's my work, and then that means that number that goes down here is roughly 247 pounds is that number that we're looking for here. Alright, now something else I want to show you guys is your calculator can do all this conversion back to x for you, just like it can you can plug in the z-scores and find out what the area is between two z-scores. You can plug into x values and find the area between the two x values, or you can plug in an area to the left in a regular distribution and find the value that has that area to the left. So let me show you a slight alteration to your calculator that lets you do these same probabilities without converting to z-scores. So I go into the normal CDF. If I'm finding an area or probability, that's normal CDF's job. So normal CDF, lower number again, we'll just use a big negative number, negative 99999, when that shaded area goes all the way into the tail. And then where does it stop? It stops at 174 in the original distribution. Okay, now normally we close that off, right? But if we are not dealing with a standard normal, we can tell the calculator by adding another comma and then giving it the mean and the standard deviation. If it's something other than 0 and 1, we can tell it what that mean and deviation are. Alright, and there's our answer. Notice it's a little bit different here, 0.52749, which would round to 0.5275, 0.5279. The reason again that is because this z-score was rounded. This is rounding it, but all the way down to here. It's not rounding it to a small place value. If you actually compute the z-score minus or 174 minus the mean of 172 divided by the standard deviation of 29, it's not just 0.07, it's 0.0689. So it's a little bit actually to the left of that 0.07. Alright, so we don't have as much area as we're saying when we rounded it. Alright, so the calculator is actually a little more precise and more accurate when we're doing these, but there will be from time to time discrepancies between what the calculator gives you and what the table would give you if you did this via the table. Alright, all these examples that I was showing you down here are areas found via the table in your book. But it's built in with a tolerance just in case you are using your calculator, so it would accept if you wrote in 0.5275, it would accept that here for this problem. Alright, and then we were down here doing this problem, finding the area to the left. Same thing, inverse normal. If you just put an area to the left, it's going to give you z-score. But if you give it an area to the left, and you give it a mean and standard deviation, 172 and the 29, it will convert it back to the x value for you rather than keep it as a z-score. So there's the 246.675, 246.699. Again, only discrepancies is just because they're using that number. This calculator is using many more decimal place values than this. So roughly 246.7, roughly 246.7. We'd still round the same place to the tenth and definitely to the nearest whole number when we do these. So again, the discrepancy, because of the precision, the increased precision you get from the calculator, is going to be gobbled up in the error tolerance that the homework problems allow. So you can use your calculator and not worry about the table and the calculators having that slight discrepancy in their output. Alright, but that's the inverse normal CDF. We're doing the exact same thing again. We're just adding to the very end the mean and the standard deviation.